Hello, this is Brett from SurvivalComms, and welcome back to Survival Antennas. In this episode, we're going to talk about RF feed line or transmission line. Now, RF transmission line, in this example here, is coaxial cable, but we're going to discuss many different types of transmission line. And the definition of a transmission line is you're basically moving radio frequency alternating current from one point to the other, or transferring power. We're often spoiled with the use of coaxial cable because it works so doggone well. It's flexible, it's easy to deploy, there's no real considerations for where or how you deploy coax cable. There's limits on length, of course, because there is a certain amount of loss that's inherent in the cable, and loss goes up as frequency increases. But overall, it's the most efficient solution that we have to use, on field deployable radio frequency equipment. And our typical coax cable, those of you who've been watching this are fully familiar with it. You have two conductors, they're separated from one another by a dielectric, and the outside of the cable is insulated with a jacket. It's important to remember that coaxial cable is considered to be an unbalanced feed line, meaning that it has a relationship with ground. And typically coax cable has an impedance of 50 ohms, which our output in our two-way radio is looking for 50 ohm load, so it's a perfect match for our equipment. So what we can see from our test equipment is that these matched impedances are allowing our test equipment to deliver full output power to our 50 ohm load with a minimum of reflected power. Now, our first alternate to the use of coaxial cable is going to be TV coax. Now, TV coax this has got television type of connectors, which are called F-type connectors on it, and it's a 75 ohm cable, but it provides a pretty decent match for a radio. So your first line alternate feed line, if you're a user of coaxial cable, would likely be television coax if you could find some. This is the results of having our test equipment hooked up with a section of RG6 75 ohm coaxial cable. Our worst case scenario is an SWR of a bit over 2 to 1, that our range is 1 to 3 to 1. If we want to zoom in a little bit here, we'll go ahead and zoom in a little bit to give us a better idea of the spacing of these peaks and valleys. And you can see right here. So by taking this small snapshot of RF spectrum here, which is 30 megahertz wide, we can see that our average is about 1.5 to 1, which is perfectly acceptable. This, and I've said it before, is a resource, and this is something you're not going to recreate in the wild, meaning it's not something you're going to be able to take a couple pieces of wire and put it together with some heat shrink tubing or electrical tape or something like that. It's just not going to work. So once this resource is depleted, we're going to have to come up with alternate means to feed an antenna, and that's what's going to be the subject of the discussion. Our first thing we're going to talk about is the elephant in the room, which is connecting any of these kind of feed lines to this SO239. It could be a BNC, a mini UHF. Now, our primary method of attaching a feed line to our radio equipment is with the correct RF connector that's properly terminated to the feed line. Our first level alternate method is going to be using coaxial cable and using an adapter such as what's contained in this kit right here. Unless you actually work in the radio communications field in a technical role, you probably aren't going to possess an adapter kit such as this, and certainly wouldn't have it on or about your person. But having an adapter set such as this in a small bag is certainly very useful and something you would consider. And I did a video about 4 years ago on the importance of having an adapter set and how they can help you out, and it's in my playlist. Now, when we move from coaxial cable to our contingency and emergency feed lines, we're going to end up needing something such as this right here, which is merely a binding post adapter to a RF connector. And as you can see here, we've now terminated it for a PL259. But one of these right here is useful because you can take a balanced feed line arrangement and connect it to the back of a piece of radio equipment, or you could just go ahead and put a vertical radiator and a counterpoise, making an effective back of set antenna if required to do so. An equivalent to a binding post and RF connector is going to be something like this, where you just take a short section of cable and leave your RF connector on one end of it, and then just merely attach a couple of test clips to it. Or, failing the possession of test clips at the particular time, you can just take this small section of feed line, cut it, and then just go ahead and tie these other ends into your field expedient feed line, and that will work out just fine. Now, failing the ability to gather any of the resources outlined above, we end up having to use an emergency attachment method shown here. And much like the phone company, if it touches, it talks. Just break your two coax conductors out. You can fold back your center conductor on itself to take up the space. And then, all I've done is just cut my dielectric back, and you just shove that in there, and that shims it up. Take your shield or your braid and either shove it between your chassis and the cover on the radio, or wrap it around the RF connector, or just do what I've done here. Just lay it on here, tie a simple clove hitch on top of that, and bundle some cable on it, and it makes positive contact with the chassis of the radio. Not perfect, but it works. Now, our contingency type of feeder is going to be something like this, and this may be your primary depending upon your radio setup, and this is just balanced feed line. Now, we call this balanced feed line, of course, because there is typically no relationship with ground in the employment of this feed line as designed. Our parallel feeder is considered to be a balanced feed line. Now, by balanced, it means that the voltage and current is equal across the entire line. And like in this example here, we're looking at a dipole antenna that's a balanced antenna design. Typically attaches to a balun at one end and to a balanced type of antenna at the other. Window line such as this is very popular in amateur radio. It makes for very effective multi-band antennas because there's much less loss in parallel feeder than there is in coaxial cable under high SWR conditions. So in the instance of making a multi-band dipole or any kind of multi-band antenna, having it fed with a balanced feeder provides for a more effective solution than feeding it with coaxial cable. Now, just about any tuner that's worth a salt has a built-in balun. This M-Tech here has a 4-to-1 balun built into it, and also my Dentron Super Tuner has a 4-to-1 balun built into it. Now, most of your auto tuners and stuff like that do not, necessitating you have to have a separate balun such as this. And this is a 4-to-1 and a 1-to-1. All these items you see before you that we've just discussed are luxury items. And this is survival antennas. So we don't have the luxury of luxury items. What we do have is wire and whatever the heck we've got on hand to build a feed line, pair it to an antenna, and establish an effective talk path without the luxury of these items. And all it consists of is two conductors that are parallel with one another that are separated from one another by a dielectric. Now, that dielectric can be air, or it can be a polyethylene plastic such as this right here. It can be a Teflon. There's many different varieties of that. But when it comes to making an emergency feed line that we're going to have to press into service, we're going to end up dealing with making a line as a parallel feeder because that is what we have available to us. It's going to be easy to construct. Again, trying to construct a coax cable out of the materials we may be able to come across is going to be extremely difficult, whereas making a balanced feeder is going to be much easier. An important thing to remember in regards to pre-made balanced feed line is that it's quite rare in the wild. I mean, the only place you're typically going to find something like this is going to be in the hands of an amateur radio operator. 300 ohm twin lead, which is like what we used to use in television sets before cable television, and those of you who remember life before cable television will certainly know what I'm talking about. That right there in some home improvement stores is still available, and that right there you can make feed line out of that if you can get your hands on it. But typically television coax is going to be far more likely to be an available resource to you than finding 450 ohm balanced feed line. The thing we need to keep in mind when we're using a balanced feeder instead of using coaxial cable is what's known as characteristic impedance. We already know that the output of our radio is looking for a 50 ohm load, and that radio coax provides that
pretty perfect match. And then we have TV coax, which is pretty doggone close. And then we have something like this, which is 450 ohms of characteristic impedance. And some of the examples we're going to work with are between 100 and 150 ohms of impedance when we're making our own feed lines.
Now, utilizing balanced feed line requires some attention to detail on routing the cable. Balanced feeder should not be coiled up on itself like this. This should be laid out straight. And in fact, it said that balanced feed line should not be laid upon the ground. I try to minimize that, but if some ground contact is necessary, I say roll with it. Balanced feed is sensitive to being wet, so oftentimes after a rainstorm, you're going to see your feed line change its characteristics somewhat. Balanced feed line should also be kept away from metal objects. You know, running it over something like this fence right here is not the correct way to route this. So even far from ideal, routing our feed line over this fence utilizing these field expedient insulators is preferable. So when selecting material to build our balanced feeder, we need to look for consistency. We need to have consistency in spacing. Now, it doesn't necessarily have to be as widely spaced as we see here with this 450 ohm window line, but it needs to be consistent throughout the entire length of the feed line. The conductor size should be consistent with one another, and the insulation quality should be consistent as well.
So knowing what we know now about balanced feeder and the importance of maintaining that consistent spacing between the conductors and having them insulated from one another, it's easy to see that you could use something that has two parallel conductors, such as this WD-1A military phone wire would work well. You can use lamp zip cord, you can use speaker wire, or any other conductor that consists of two conductors that are parallel with one another that maintain that consistent spacing between the conductors. You can make your own parallel feed line, like this right here is welding wire. This right here would work. The only problem with doing this is now we're going to have to cobble up some kind of a system to maintain that consistent spacing. The balanced feeder that's the easiest to fabricate and roll out is just a simple twisted pair. We've taken this out of some category 5 cable, and you can see we have two conductors and they're consistently spaced and insulated from one another by having a uniform twist across it. And having something like this allows this to function as feed line. Now, is it going to be a lossless feed line? No, not at all. This is going to have much more loss in it than a pre-engineered RF feed line such as coaxial cable or your window line, but it's going to allow you to establish a talk path with just the resources that are available to you. And also, twisted pair is the easiest way for you to fabricate a feed line out of, say, some hookup wire, for example, by just having uniform twists.
To make your own twisted pair out of standard hookup wire is pretty doggone simple. Just take the desired length of it, whatever you have, and just fold it evenly on itself, and then place it around an object, such as this pipe. And at this point, all you do is just make simple, even twists. And you want to make sure that you're twisting both ends of the cable and that your twists are fairly consistent and fairly even. And your finished product should be something like this. I mean, you just want it to be fairly consistent. The following and the formulas presented herein have been kind of an amalgamation of my own experimentation here, utilizing like this 50 ohm dummy load to simulate an antenna, and of course our cables under test utilizing a couple of binding post adapters. And basically we're just sweeping this line here and noting the changes that occur based upon frequency versus wavelength of the feed line, and then trying to calculate what the velocity factor of the line is, and we'll get into that earlier or later on. And the information gathered from Module 10 of the Naval Electrical and Electronics Training System. An important consideration when making your own feed line out of like this WD-1A wire is its size matters, and that you need to make sure that you cut your wire to a specific length when you're direct feeding a resonant antenna. And the reason why is because this feed line acts as a shorted line. When the impedance of the load, like let's say a 50 ohm antenna, and then you've got 150 ohms of characteristic line impedance. It's less, so therefore it acts as a shorted line. So your lines need to be cut at even integer quarter wavelength multiples. This illustration here does an excellent job of showing you exactly what I'm talking about here. You can see that at a quarter wavelength, which is an odd integer multiple, that we act as a parallel resonant circuit and have high resistance. This high resistance is going to make it harder to achieve a match with our 50 ohm load to our 50 ohm equipment. So if we do a half wavelength, you can see that it acts as a series resonant circuit and therefore has less resistance in it and will allow it an easier match to direct feed that 50 ohm antenna. Just as length matters, speed matters. So in order to determine the length of our feeder, we need to know how fast it's traveling. Radio waves propagate at the speed of light in free space, and that's where 492 divided by the frequency in megahertz comes from, which is in our left-handed column there. When you take a radio wave or electromagnetic wave and you confine it to a conductor, the distance that it travels is reduced by the amounts shown in that left-hand column. And this is known as velocity factors. And you'll often see that when you're looking at cable specifications for feed line. If you look at the column on the right here, you'll see 468 divided by the frequency in megahertz, which by this time, if you've been watching this series, should be very familiar with you. That's our single formula that we utilize for the Survival Antenna series. Now, I've taken rough rule velocity factors, which make it much simpler for you to do your calculations on determining how long your feed line needs to be. Each one of these feed lines is electrically 1/2 of a wavelength long. And you can see that their physical length is much different than their electrical length. That line on top is a 450 ohm feeder. If we are very careful to cut that feed line to even integer quarter wavelengths, like a half wavelength, a full wavelength, etc., etc., so it's a closer match to our equipment, and our equipment is actually going to transfer its power more efficiently to the load that we've built. Now with these smaller lines down here, the coaxial cable isn't that big of a deal. However, if we're making stubs and we're making a balun out of coaxial cable, we're going to have to pay attention to its electrical wavelength. And when we look at our twisted pairs here, if we want to make it as efficient as possible, paying attention to these lengths that you're going to cut it to will assist you. Okay, let's do a little experiment here. We've taken an NMO mount and we've attached it to 17 foot of coax from the NMO kit. The antenna that we're using for the test is a dual band VHF-UHF antenna that I made from two 800 megahertz 5/8 wave antennas, and I have a video on how to do that in my playlist as well. Our first test is just to check and see what the SWR is of our antenna with coaxial cable feeding it, and as you can see here, we're looking at it being somewhere in the neighborhood of 1:4 to 1 in the center of 140 to 170 megahertz. Here you can see the performance of our reference VHF antenna fed with coaxial cable, and on our reference VHF frequency we're going to utilize for this test, and the received signal strength is less than -90 decibel milliwatts, somewhere on the order of between -87 and -89 decibel milliwatts of received signal strength. Before we cut our feed line, we need to determine how long we need to make it. Apply our simple half wavelength dipole formula, 468 divided by the frequency in megahertz. We're making this for VHF, 146 megahertz, 3.2 feet long. Now we apply our velocity factor rough rule of 0.6. So we take 3.2 feet, multiply that times 0.6, and come up with 1.9 feet. So we know that it's 1.9 feet per half wavelength adjusted for the cable in use. So let's say we need 15 feet of feed line. We know that a half wavelength is 1.9 feet at the frequency of interest. So merely take 15 and divide that by 1.9, and that gives you 7.89. Round that up to 8, and rounding is perfectly acceptable for use in this field rough rule calculation. And now we know that if we cut off 15 feet of our Cat 5 cable here and removed a twisted pair, that is going to be an even integer at a quarter wavelength, so we're good to go. Now we're going to go ahead and remove our Cat 5 cable. Just remove a few inches of insulation with your Leatherman tool. And then just grab a hold of that string and pull that string. And as you pull this string out, it strips away your jacket. So merely select a pair from your 4 pairs available, and that's going to be your feed line. Remove it from the bundle. Now we have our new feed line attached to our ground plane. And we'll just go ahead and reattach our antenna and give her a whirl. So receive performance on our reference station on VHF is about the same. It's running between minus 86 and minus 90 now, and before it was minus 86 to minus 89 decibel milliwatts. This is what's so cool about radio. Now look at this interesting SWR curve here. Okay, we're running from 140 to 170 megahertz, and instead of basically being, you know, our normal dip like this, we end up having this kind of really narrow null and another narrow null on the opposite side of this peak, which is kind of interesting. But it looks like we're resonant right where we want to be. Well, let's put some power through this thing and get this party started. We got our noise generator here feeding into our tail wave meter, and then I've got a small jumper with alligator clips that's tying into our Cat 5 twisted pair, feeding the SurvivalComms homemade dual band antenna. Alright, we'll start with forward power. Forward power is just a tad over 4 watts. And our reflected power is about 0.2 of a watt. So that's going to be 1.5, 1.6 to 1 as far as an SWR ratio, which isn't bad considering that, you know, it's what we're using for feed line here. Alright, same antenna configuration as before, except now we're using my Astro Spectra in a box. And we've got our ranges set correctly. Let's see what happens here. Got 40 watts forward. Looks like about 2 watts reflected. So what that means to us is that we're less than 2 to 1. So this setup in and of itself is usable. So what we've seen from our testing is that Cat 5 twisted pair will work as an RF feed line if it had to be pressed into service as such. Now I wouldn't recommend running a lot of power through it, however. Now we saw that it did tolerate the power of a mobile radio. I don't believe that it would tolerate it for a prolonged period of time though. I think that keeping your power level around HT levels, I think that it would work just fine. Would I replace coax cable with Cat 5 twisted pair? Absolutely not. But again, if you had to press this in service, I think you'd be good to go. Now we're testing our homemade 16 gauge twisted lead that we made out of hookup wire. And it looks like our bandwidth has gotten much wider than it was with the twisted pair out of the Cat 5 cable. So the larger diameter conductor has made a difference in our SWR bandwidth. See how our 16 gauge twisted pair handles power. I'm going to start with an HT, 4.5 watts forward. Barely moving the needle in reflected power. Well, let's see how our homemade twisted pair handles mobile radio power. 40 watts forward. Barely moving the needle on reflected. So it's obvious that the larger size conductor handles RF better than the Cat 5 twisted pair.
3 years ago I did a video about making a simple HF wire dipole out of WD-1A military phone wire, and it's really easy. All you do is take a section of WD-1A wire, measure down a quarter wavelength on that wire of the frequency of interest, split that out, and with your 2 conductors right here, and now you have your dipole elements. Tie a simple overhand knot where your feed point's going to be. To determine the length of your feed line, it's really simple. All you do is it's any even integer multiple of a quarter wavelength. Then multiply that times 0.6 and so on and so forth. So I think it's easy to see from that dipole I just showed you how any of these other antenna designs that we've been working with in the Survival Antenna series would certainly work with balanced feed line. It's my hope that those of you who have been watching the Survival Antenna series have found this content to be useful, and I encourage each and every one of you that's been watching this to work along and build these projects yourself and work out your own solutions that you can apply when you need to apply them. I hope this helps. This is Brett from SurvivalComms. Till next time.